So that's the basic idea. So let's actually take a look at some of the under the hood, like how does this work mathematically? And like what are we actually doing? So offline, when you simulate a model, right, it's a mathematical equation that represents that model, right? So you're going to design your power systems and your controls, and then you're going to turn those into the differential equations, which you can then linearize and discretize to actually solve, right? You need to choose the order of your solver. You need to actually select that. So we do this same process in offline or in real time, where we take the design, we generate our equations, and then we turn those into solvable numerical ODEs and PDEs. When you do that in offline, it just goes as fast as possible. So if it's very simple, it goes quite quickly. But if you imagine if you had like an 8th or 9th order numerical ODE, it might be very slow. If you did like a 1st or 2nd order, it might be much quicker. But it just goes as fast as possible because it doesn't have any physical boundaries. It doesn't care. It just does the time step. For those of you who know about this more in depth, you might know about variable step solvers and how it can kind of reiterate those steps. Basically, it's just going as fast as it can to simulate that. But in the world of HiL, we don't have that luxury. We have to match one-to-one real time. So if you wanted to create a sine wave in the real world, for instance, we actually have to model that as a series of points because we're solving it mathematically, an ODE, over a time step. So we actually generate and solve each of these points through a model. So what you can do and how you can imagine this is we have to use fixed time steps. So we say every 50 microseconds, every 25 microseconds, there will be a new data output. We can go even as low as a few nanoseconds. We can generate signals up to megahertz frequencies like PWMs and things like that. So the fixed step of the computation, it has to be respected. You can't go outside of the bounds. And if there's time left over, the simulator just does nothing for that time because it has to wait for the system to respond. If it just tried to start the next step, it means it'd be going faster than real time. And so suddenly the physics wouldn't work between the real world and your simulation system. So we synchronize this clock with the real world. For those of you who know about like UTC time and like standardized time, we can actually timestamp each of these seconds down to that nanosecond level. So you know the time of your simulation matches epoch time. So you have this like one-to-one connection. So what this would look like is this is the reality. The world around us is continuous. And what happens is we represent it as a series of points. There are ways to interpolate, so you can smooth and things like that. But at the base level, every HiL simulation represents reality as a series of points. And so you need to be aware, how many points do I need? If you imagine a sine wave, right? If you have 1,000 points, you're going to get a really good sine wave. If you have 4 points, not so much. So this is what this looks like. We have to pick. So if you look at a dynamic signal like this, we have to cut it evenly throughout the length of that. It's also like that's universal for all HiL. So if you ever see like Typhoon or another manufacturer, it's going to be the same thing. But like we said, be very aware because in offline simulations, in this step, your computer is going to make more stages because it doesn't care about the real world. So it can recalculate it until it's accurate. We can't do that in real time. So you need to be aware, and this is one of the key challenges, is knowing what's fast enough. One of the easiest solutions is just throw more power at the problem, throw more computational resources. Sometimes that's not enough, though, when you're doing huge grids of the entire Western United States or all of the Great British Grid. So you have to be smart. But this is essentially what we're doing, is we're taking what we want to represent of a true physical system, and we have to cut it to get as much of that signal as possible. So in the same way, if our pulses or our signals are too small, they're going to get lost in the noise because we can't, again, cut this into smaller pieces. So again, that's the thing. When you're talking about HiL, it's consistent throughout the entire process. So we're trading off between different setups. For scale, electromagnetic transients, it's going to be microseconds. You might even have nanoseconds. Mechanical time, it's going to be in the milliseconds, and then thermal systems are seconds. You can do models that are called multi-rate. So if you have a thermal system, a mechanical system, an electromagnetic system, and then a power electronics, each of those can be done at a different rate. And then the system overlaps them to produce like a combined image. And so what you want to do is you want to make sure your simulation ends up like this. So you capture that dynamic response accurately. So how does it actually look in practice? So we talked about your simulation is running some physics model. It's talking to a controller back and forth. So let's say this is an inverter or whatever it might be. You have your device. Your simulation is going to read inputs. For instance, the PWM signal. It'll take in that PWM signal. It'll see the duty cycle, the frequency, all the information. It'll then input that to your inverter model, and it will calculate, okay, if this inverter is receiving this PWM, this is how it's going to respond. It's then going to map those signals to the output, so the physical world. The math happens on the CPU, and then it has to map them to an SFP channel, an analog channel, a digital channel, and then output those signals. Those go into your controller, so it might be a signal, voltage, current readings. Again, these are simulated signals. So I'm going to process that, whatever the microprocessor is going to do, and then it will output and it will send back. And this happens one-to-one. So they're going to constantly be sending data from one device, which has the physical model, into the controller. This is simplified. You can have many controllers, many devices. You can have, we've seen some with dozens of different devices all connected together. We have some simulated controller code. So you don't have to do all your controller code here. You can build a controller that's just simulated, and that simulated controller can manage parts of it, and you can have real controllers. So this is a basic model, but you can be as flexible as you want with this to get this set up. So these are the basic steps. Looking at that at a base level, this is what it looks like. So in, again, fixed time step, that happens consistently every 50 microseconds, 25 microseconds. Your simulator is going to measure what it reads: PWM signals, analog signals, data signals. It's going to then use that with the physical model to compute the next step. It'll then output that. So it does this every clock cycle that you set for your simulation, and this controller does whatever it's going to do with that data. So what happens if we go over? Doesn't work. It's called an overrun. It means your time step is too small or your computation is too complex. You need to rearrange it because now one period has stretched into two. The system will try to recover itself, and it often can. You can see simulations that have an occasional overrun, and it's not the end of the world, but they can also basically destroy your results because you've missed a step. So in high dynamic moments, you're going to miss one of those data points. It's not going to work properly.